discuss completely the doubly reinforced sections and also T-beams, both theory and also numerical problems. I will complete this within 2 hours. Doubly reinforced beam. So far we have seen singly reinforced beam where the reinforcement is provided only on the tension phase to take up all the tensile stresses that are acting on the structure on the tension phase. And here it is another member, doubly reinforced member. Why doubly reinforced member is required? You know, there are three different types of sections in singly reinforced. One is under reinforced sections, balanced section, and third one is over reinforced section. The moment carrying capacity of over reinforced section is same as that of moment carrying capacity of the balanced section. So that means any increase of steel reinforcement in a limit state method of design, there is no increase in moment carrying capacity. That you have seen in the last class. When the graph is drawn between the moment carrying capacity and percentage of steel reinforcement up to certain percent, that is equal to the balanced percentage of steel reinforcement, the moment carrying capacity increases continuously and thereafter it is constant. So that means any additional steel reinforcement that is provided on tension phase will not carry any additional moment. So that's why to increase the capacity of the given beam, it is required to increase the compressive resistance of the concrete. Because when in the case of in case of balanced section, the AST balanced is the balanced reinforcement that is exactly equivalent to the compressive resistance of the concrete. But once the steel reaches its balanced value, the entire concrete in the section utilized. So to increase further steel reinforcement will not increase moment carrying capacity because T may be more, but compressive resistance is not going to increase. So because of that reason, to increase the moment carrying capacity of the section, we are going to provide compression reinforcement on compression phase of the section. So that the compressive resistance is by means of the compression steel reinforcement and compression zone of concrete. So to increase the moment carrying capacity, we are going for compressive reinforcement in addition to the normal tensile reinforcement that is provided. So that is the major purpose of providing it. In the last class, you have also seen when bending moment, when moment acting mu is more than mu limited, there are two different options. One option is either you have mu means what is mu? Moment, bending moment or ultimate moment. Ultimate moment based on the loads. Ultimate load based on the loads. Whereas mu limited means ultimate moment carrying capacity of the section. Ultimate moment carrying capacity of the balanced section. So that means if the moment due to load is more, then the options are only the two options. One is increase the size of the beam, so that mu limited also increases. The other way is by providing doubly reinforced section. That is providing the reinforcement on compression phase also. That is why doubly reinforced beams are required. So what situations doubly reinforced beams are required? You can have some examples where doubly reinforced sections are required. When the moment to be resisted by a singly reinforced beam is more than the limiting moment of resistance. That is this case. For this case, you can look at here the first diagram. ASTB, balanced section. Area of steel reinforcement for balanced section Corresponding to this, the moment carrying capacity will be MU limited. If you provide AST more AST than ASTB, you can look at here, AST is more than ASTB. That means by providing more steel reinforcement, the moment carrying capacity is also MU limited. That means because of increase of steel reinforcement, there is no increase in moment carrying capacity. There is no increase in moment carrying capacity. So what are the other alternatives? The other alternatives are by increase the size of the section. If we increase the size of the section, the compressive resistance contribution of concrete is more, and compressive resistance will be more, tensile resistance also more, the load carrying capacity or moment carrying capacity of this beam will be more. So you can observe from the first two diagrams, the size of it will be more. This is one option. The other option is the same size of the beam, with providing area of the compression steel reinforcement on the compression side. So that is called the doubly reinforced beam. And in this case, M is more than M limited, we can go for doubly reinforced section. So that means sometimes where there is a limitation of the depth, then we go for a doubly reinforced section. So this is the concept of providing compression reinforcement for the beam. And another situation when the depth of the beam is restricted due to architectural and aesthetic reason. So sometimes the overall size of the beam is restricted and the moment carrying capacity should be more. In such cases, there is no other alternative except by providing compression steel so that the compressive resistance of the section will be more. So this is another situation where we go for doubly reinforced section. Next, when the beam is subjected to reversal of stresses. Reversal of stresses means, for example, now because of the dead load, a member is under tension. You can look at here, a member bottom is under tension. And because of wind force on a member or any earthquake force on the member, the same point may be under compression. Or otherwise already compressive area now changed to tension. So that means tension zone is changed to compression. Compression zone is changed to tension. That is called the reversal of stresses. So that means in one stage tension is at bottom. So we need reinforcement at bottom only. But at another situation, tension is at the top, you need reinforcement at the top. That means for both the situations, the beam must be in safe condition so that reinforcement is to be provided both at top and also bottom to take care of the tensile stresses because of the reversal of stresses. So that means due to loading, different loads that are acting on the structure, in one particular time, the tension phase may be changed to compressive phase. The compression phase may be changed to tension phase. Such a situation is called the reversal of stresses. And when reversal of stresses are expected, then naturally reinforcement to be provided both on top and bottom, so that compressive reinforcement and tensile reinforcement can be sometimes reversed. And another situation is for continuous beams, tensile stresses induced at the bottom near midspan and at top of the supports. If this is the continuous beam, bottom face is under tension. You can look at bottom face is under tension, top is under compression. So the main reinforcement is to be provided at the bottom. Whereas over the supports, the main reinforcement is AST provided at the top. So, and we cannot provide the reinforcement only at the required distance because it has to satisfy bond requirements, shear requirement and all other requirements it has to satisfy. So we cannot put the reinforcement in exactly pieces. One piece for at the support, another piece here, one more piece at that level. We cannot provide the pieces. That's why the continuity of the bar, some of the bars are continuity throughout, either at bottom or top, even at the bottom also. At mid span, it is tension, so we provide AST. And at the near the supports, it is a compression. It is near the support. It is compression. And code also says that one third of the main reinforcement should be extended into the supports. So because of considering all these points in view, there is a reinforcement, continuous reinforcement is required, and more reinforcement is provided wherever it is required. So that means more reinforcement is required exactly over the supports at the top, and exactly at the midspan at bottom, and all remaining parts we can provide minimum quantity of reinforcement. So for such a practical situation, we need doubly reinforced sections. So at any level, there is a top reinforcement and also bottom reinforcement, so that the beam that is designed for continuous beam should always be doubly reinforced section. And sometimes what is going to happen, the structure is not only subjected to bending moment, it is also subjected to shear force. And we have to design the beam for shear, so that beam has to resist all the shear stresses that are induced in the structure. So in such case, how to provide the shear reinforcement? It is to be provided in the form of a links, or otherwise it is in the form of a stirrups. It is in the form of a stirrups, rectangular stirrups. And we cannot simply keep rectangular stirrups as we like in the concrete along the member. So there must be in proper position. All these stirrups must be designed vertically. So vertical stirrups, or if the stirrups are designed inclined, exact inclination must be provided. That is possible only when there are hanger bars. Though the reinforcement is not required, we need to provide some minimum reinforcement at the top, so that all these stirrups will be kept in proper position. So for that purpose, anyway, we are going to use hanger bars. That hanger bars itself will be acting as compression reinforcement, and this is also called a doubly reinforced section in practice. And by providing doubly reinforced section, the ductility of the beam increases by providing both reinforcement in tension phase and also compression phase, and it absorbs more energy. So because of all these reasons, the doubly reinforced sections are required. And in practice, even for a small beam, the beams are always doubly reinforced beams, because for providing the shear reinforcement in proper position, hanger bars are to be provided at the top, not at the top, at the compression zone also, so that these bars will be acting as compression reinforcement. And while designing the structures, particularly for the design of beams for flexure, the hanger bars can be taken into consideration for computing the compressive resistance of the section. So in practice, we may not observe singly reinforced beams, because for every beam there must be a hanger bar and also the stirrups. So in practice, all the bars, all the beams are with the reinforcement both at top and also bottom. So it's always better to go for design of a doubly reinforced beam instead of singly reinforced beam. Now, the doubly reinforced beams are used when I told you in detail, when the depth of the section is restricted, and restriction of the headroom, the span is very long, reversal of stresses takes place. So because of all these reasons, we are going to provide the doubly reinforced sections. And you can look at here, in the compression zone. Minimum steel reinforcement will be provided, whereas in the tension zone, we are going to provide steel reinforcement as per the design. And one third of the steel reinforcement must be extended into the support. so that continuity of the bars both at top and bottom are required. So by providing continuity of the bars both at the top and bottom, then the section at any point is called the doubly reinforced section. And analysis of doubly reinforced section. So here, understanding this concept is more important. If you understood this concept, all these diagrams, everything is over. It is this analysis is exactly a small extension to the singly reinforced section. Already you have seen clearly the beam cross section, the strain diagram, and also the stress diagram for singly reinforced balanced section, singly reinforced section. Now it is extension. What is that extension? What is the difference? The difference is only by providing the compression steel reinforcement on the compression face. So the whatever the analysis that we did in singly reinforced beam, it will be the same, will be considered as it is, and also by providing, by adopting, by considering ASC into account, area of the compression steel reinforcement into account. So don't worry about it. Try to understand each and every diagram, and most of the diagrams are similar to the previous one only. Now you can look at the first diagram. It is doubly reinforced section. Doubly reinforced section. So it is a section of overall depth D and width B, effective depth D, having steel reinforcement tensile AST, and ASC is the area of the compression steel reinforcement. This is the overall doubly reinforced section. And whatever may be the section, one of the basic assumption is the strain is proportional to the strain. The strain is proportional to the distance from the neutral axis. One of the assumption in limit state method of design is this, and the strain diagram is always the same. So this diagram is same as that of used for singly reinforced beam. So x is the depth of the neutral axis. So instead of x, you call it xu, and it is d minus xu is the depth of the neutral axis. Overall depth minus depth of the neutral axis, that is the distance of the tensile reinforcement from the neutral axis. So this is the notation for the strain diagram. For the strain diagram, the maximum strain in concrete is EC, that is 0.0035. And at the bottom, strain in steel, that should not be less than 0.002 plus Fy by 1.15 ES, that you know. So this is doubly reinforced, you know. This diagram is already known, what it is same as that of the singly reinforced strain diagram. There is no change in it. So now this doubly reinforced beam is identically equal to the entire concrete. You can look at the entire concrete here, entire concrete, and AST1. So originally the steel provided at tension phase is AST, but we are considering only AST1. What is AST1? AST1 is the area of the tensile steel reinforcement required for balanced section. So that means this is called the singly reinforced balanced section. This is called singly reinforced balanced section. So singly reinforced balanced section. What is the remaining? Already the total concrete is considered here. So what is the concrete part now? There is no concrete at all. You can assume the imaginary beam without any concrete, the dotted line, the imaginary line, dotted line, so that there is no concrete, because the entire concrete is taken into consideration in the first diagram. And what is the remaining steel AST? Already AST1 is considered here. Rest of the steel, that is called AST2. AST2 will be considered here. So that total steel AST1 plus AST2 will be equal to AST. Okay. AST is now split into two steel reinforcement. One is area of the steel reinforcement for balanced section, and another one is the remaining steel reinforcement on tension phase. So what is the remaining in the doubly? The ASC. Whatever the ASC left over remaining, the same ASC is considered here. So that means original doubly reinforced beam can be split into a singly reinforced balanced section plus only compressive steel reinforcement and also extra tensile steel reinforcement. Extra tensile steel reinforcement. And you know that this is singly reinforced section. Already you are familiar with singly reinforced section. And what is this CC called? CC called compressive resistance of the singly reinforced balanced section. What is compressive resistance of singly reinforced balanced section? That is 0.36 FCK B into XU maximum, because it is for balanced section. It is for balanced section. CC is that one. And what is T1? T1 is nothing but what is the area? 0.87 Fy AST1. That's all. What is T1? T1 is nothing but 0.87 Fy is the stress multiplied by area is AST1. That's all. Okay, you can look at here AST1. 0.87 Fy AST1. And this is CC is nothing but 0.36 FCK B into XU maximum, because it is balanced section. And after that means this is the stress diagram. Already you know the top is 0.45 FCK and it is a parabola rectangular initially and then parabola portion. And again for compressive steel and also for tensile steel, compressive force corresponding to the compression steel is CS. CC means compressive resistance of concrete. CS means compressive resistance of the compression steel reinforcement. CS means compressive resistance of the compression steel reinforcement. And T2 is the tensile resistance of the extra steel reinforcement. Tensile resistance of the extra steel reinforcement. What is T2? T2 is nothing but 0.87 Fy into AST2. Here AST2, you write this. And similarly CC. What is CC value? What is the magnitude of CC? Or what is the magnitude of CC? That is nothing but FSC minus FCC multiplied by ASC. So that means what is going to happen here? FSC ASC means compressive force minus FCC. What is FCC? FCC is concrete strength. That means by providing compression steel reinforcement, we are replacing some concrete. We are replacing some concrete. That's why it is FSC, stress in steel, minus what is that replaced? Replaced material is concrete. So FSC, compressive strength of the compressive strength of the concrete, FCC. FSC minus FCC into ASC is CS. So that means ultimately the doubly reinforced section is split into singly reinforced balanced section, and another one is additional tensile steel and also compression steel, and these two are the stress diagrams. That's all. If you just understood these diagrams, everything is over. Everything is over. Now you look at here, this is the doubly reinforced section, already you know it, and it is the strain diagram for the doubly reinforced section. ES should always be more than strain in steel. Strain in steel should always be more, or otherwise it should not be less than, because it is one of the assumption. And maximum strain in compression steel is 0.0035. So in case of the singly reinforced section, what you have seen CC. What is CC? Compressive resistance of concrete is 0.36 FCK B into XU maximum. Why XU maximum? Because it is balanced section. 0.36 FCK B into XU maximum is CC. What is the additional term? Additional term is because of the steel, compression steel. So for that CS where it is acting, it will be acting exactly at the center of the compression steel, which is FSC minus FCC into ASC. Already I told you. So these are the two compressive forces. Earlier in singly reinforced, only one compressive force. Now the compressive force because of the steel reinforcement also appears. And regarding the total tension T equal to 0.87 Fy into AST, because here AST means AST1 and also AST2. So this is the overall base concept, and from this you can develop any number of equations for designing the structure for doubly reinforced section. Now already you know that strain should not be less than this, and in case of singly reinforced section, how to calculate the depth of the neutral axis. In the case of singly reinforced section, we have used C equal to T. Now it is doubly reinforced section. In the doubly reinforced section, what are the things here? You can observe here. This is the area contributing for the compressive resistance. And what are the things here? One is concrete, another one is steel. One is concrete, another one is compression steel. So that's why in place of C, we are now writing CC, compressive strength of concrete, CS, compressive resistance of the compression steel reinforcement, which is equal to T, Now what is CC? The same as previous, 0.36 FCK B into XU plus CS. CS means FSC minus FCC into ASC. FSC means compressive stress in compression steel reinforcement, minus FCC means compressive stress in concrete, because this concrete is replaced and providing compressive area. So that's why FSC minus FCC into ASC, which is equal to T. What is T? 0.87 Fy AST. So by using this equation, you will get the depth of neutral axis. In the previous case, what we did, the same procedure for calculating XU. Now the additional term is FSC minus FCC into ASC will come into picture as CS, and basing on that, get the value of XU. Once the XU value is known, then find out the different types of sections. This FSC value is depends on the compressive strain in steel reinforcement. See, always stress is completely depending on the strain. If the strain is more, compressive stress is also more. If for case of mild steel Fe250, FSC can be taken 0.87 Fy. FSC can be taken 0.87 Fy. You know that we are using Fy as for any material, say 415 as it is, Newton per mm square. But FSC is not 415 in Newton per mm square. What is that value? Because why it is taken 415 Newton per mm square? Because the strain in steel not less than this value. When the strain is not less than this value, the stress corresponding to that will be equal to 0.87 times of Fy. 0.87 times of Fy. So that's why wherever Fy is there, we are using 415. Whereas in the case of FSC, you should know what is the strain in it, because this is the strain on the tension phase, and corresponding to this strain, the stress is computed. That strain will be equal. The stress will be equal to 0.87 times Fy. But whereas in case of compression steel, we do not know the maximum strain value, because in the in this strain diagram, the top surface is 0.0035, and at this point it is less than 0.0035. But for example, for Fy 415, what is the strain here? Strain here will be 0.00380 is the strain. In the last class, we know how to compute the strain values. That is shown in this fashion. Okay. So 0.0080 In this case, we are using 415. But here, if you know, at the top itself is 0.0035 and slightly lower, this strain will be less. Accordingly, the stress is not 415, it is also less than that value. It is also less than that value. Whereas in case of mild steel, Fs is also equal to the same value, because in case of mild steel, what is the strain? In case of mild steel, what is the maximum strain? 0.00109, approximately 109. Last class I have seen. So at this strain itself, the stress is 0.87 times Fy for mild steel. But you can observe at the top 0.0035, here definitely the strain will be more than 0.00109. So that's why if the grade of concrete is mild steel, without any hesitation, FSC can be taken as 0.87 times Fy. Whereas if you consider Fe 415 or Fe 500, the value is not 0.87 Fy, it is depending upon the magnitude of the strain. That we will see little later. This is the diagram given in IS 456, and based on this diagram only, in the last class we have seen one table for computing the various strains at different values. You can look at here 0.002. What is the stress value corresponding to this? Similarly, here strain is 0.001. Some magnitude of the stress corresponding to that will be this. Like that, it is given as per IS 456. It is given as per IS 456. And accordingly, we have to compute the numerical values of the strains basing on the strain diagram. In the last class, we have computed the strains and also stresses, and I have given a systematic table for the relation between the stress and also the strains. Okay. Now, what is the strain in compression steel? What is the strain in compression? Because stress is always depending upon the strain. What is the strain here? What is the strain? You can look at the diagram. You can look at this diagram. This is the value of the strain in compression steel. So you can call it as ESC. ESC means strain in compression steel. So what is this distance? What is this distance? This distance is nothing but, this vertical distance is nothing but XU minus D dashed. You know that this distance will be equal to D dashed, effective cover to the compression reinforcement. So what is the strain at this point? So at that point, you know, your ESC, strain in steel, that means this line divided by vertical distance. What is that vertical distance? XU minus D dash. You can look at XU minus D dash is the vertical, which is equal to 0.0035 divided by the corresponding value of it will be XU. So that means strain in compression steel is 0.0035 into XU minus D dash by XU. So this is the simple relation obtained from the strain diagram. Sometimes this may be the question for 2 marks. What is the compressive strain in compression steel reinforcement? By giving all other parameters. So every formula is developed based on this only. You can look at here. Just now you have seen 0.0035 XU minus D dash by XU, and this also can be written XU by X1 1 minus D dash by XU. So this is the formula to be used for computing the strain. Once the strain is known, you can find out the stress in the steel corresponding to that strain based on the curves given in IS 456. Now Already the XU maximum value. What is XU maximum value? It's already fixed. Already in the fundamentals we have seen for FE 250 0.53D, FE 415 0.53D for FE 250, 0.48D for FE 415, 0.46D for FE 500. So these are the magnitude of the limiting depth of the neutral axis for three different grades of concrete or three different grades of steel reinforcement. So XU value, how do you calculate XU? XU can be found based on this procedure, equating the compressive force and also tensile force, find out XU. And based on this formula, you can also find out XU maximum. Then if XU is less than XU maximum, the type of section is under reinforced. Whenever it is under reinforced, movement is governed by T into Z. T into Z. So 0.87 FYAST T minus A. So because here T into Z means, what is Z? Lever arm. Lever arm means, so here in this case, what is lever arm? You can look at one is top one CS, bottom one CC, and middle arrow is C. Middle arrow is C. So from middle arrow to the top, it is nothing but small a. Small a. Small a means distance of the resultant compressive force from the top fiber. So that this distance will be equal to D minus A. D minus A is the lever arm. So what is A value? A value is the center of gravity of CC and also CS. Center of gravity of CC and CS. So for that distance of the resultant of compressive force from extreme compression fiber. So what you do? CC. CC is the compressive resistance which is acting at a distance of 0.42 XU. In the last class also I have seen it. And CS, compressive resistance of steel, is acting at its effective cover distance divided by CC plus CS, and ultimately you will get, by substituting numerical values, you will get A. This A is nothing but D minus A. If that this A can be substituted here and calculate the moment of resistance. Okay, or otherwise, because in the doubly reinforced section, it has its own unique feature. In the doubly reinforced section, what is that we are contributing? Any movement is sum of the moment mu1, because moment corresponding to this section is mu1, and what is the moment corresponding to this? It is nothing but mu2. So what is the final moment? Final moment is mu1 plus mu2. So what you do, whether it is under reinforced section or over reinforced section, this is nothing but always a balanced section. And whether under reinforced or over reinforced, that depends on the ASC and also AST. ALC and also AST. So in the examination, for the case of simplicity, you need not use this particular equation. You can also use this equation. Though it is under reinforced section, you can also use this equation. Because in this case, the first part is mu1, which is for the balanced section. The second part is only for the compression resistance of the steel reinforcement. So first part can be 0.148, 0.138, 0.133, etc. can be put. So only the difference here is when it is under reinforced, we are going to substitute this XU value here. I'll write once again for under reinforced case, or otherwise we can into D minus D dash. So you can use this formula for finding the moment of resistance, or otherwise this. Both the ways you can use, either that way or this way. And similarly, if XU is greater than XU maximum, This is called the over-enforced section. Though the section is over-enforced, we are going to limit XU is nothing but XU maximum. For example, if first one is 255, the second one is 241. So which numerical value is to be used here? We have to use only 241 because the depth of the neutral axis is always limited. And already I told you several times, moment of resistance of the over-enforced section is same as that of the balancer section. So when it is over-enforced, use this formula. So in total here, if the section is under enforced, moment is governed by the tension steel, and you can use the formula. Or otherwise also, you can use 0.36 FCK BXU C multiple. That means it is nothing but compressive resistance into lever arm, compressive resistance of steel multiplied by its lever arm. That's all. So it is possible only in case of doubly reinforced sections. And another type, that means in the examination the questions may be what is the depth of the neutral axis, that may be the question. Or sometimes if it is under reinforced section, what is the moment carrying capacity of the section? If it is over reinforced section, what is the moment carrying capacity of the section? These are the three possible questions that will cover with this theory. So it is completely extension to the previous one. In the previous case, the first term is there, singly reinforced. We are adding second term. Similarly, here also first term is there corresponding to the singly reinforced. We are adding only the second term. Now, design. Design means for computing the area of the steel reinforcement. You know, total steel reinforcement is AST1 and also AST2. What is AST1? AST1 is area of tensile reinforcement required for singly reinforced balanced section. Already I told you. MU limited is limiting moment of resistance of the singly reinforced balanced section. So here it is corresponding to MU limited, the reinforcement will be equal to AST1. AST1 is the area of the steel reinforcement corresponding to the balanced section. That means when AST1 means the corresponding moment is MU limited. Or when MU limited is there, the corresponding steel will be equal to AST1. So these are two associated values. Okay. So AST1 is for basing on this. And once you know MU value, if 0.87 Fy AST1 into D minus 0.42 XU, by using this particular equation, you can find out the AST1 value. AST1 is equal to, can be obtained by equating MU limited. MU limited will be equal to moment due to tensile steel reinforcement, and accordingly you get the value of AST1. And once AST1 is known, then you can find out the area of the steel reinforcement in excess of the singly reinforced balanced. Or otherwise you can, you know that already, MU means MU1 plus MU2. What is MU2? Original MU minus MU1, and MU2 is moment of resistance of the additional steel. Moment of resistance of the additional tensile steel. So T2 into Z, that is 0.87 Fy AST2 D minus D dash. So by using this, you can find out AST. Or otherwise, you can also know that in the second diagram, you know that it is CS, compressive resistance of the steel, and this is T2. That means compressive resistance of steel is equal to tensile resistance of the steel reinforcement. So you can also use in this particular way. So MUZ means here T2 into Z. Z is the distance between these two. Either you can write M means MU2 means T2 multiplied by Z, or otherwise CS multiplied by Z. T2 multiplied by Z or CS multiplied by Z. So T2 multiplied by Z means this, CS multiplied by Z means this, and you can find out the unknown parameter ASC. ASC. And once ASC is known, from this equation you also known CS will be equal to T2. CS equal to T2. That you can see next page. You can look at T2 equal to CS. What is T2? 0.87 FY equal to CS. CS means FSC minus FCC ASC. From this you can find out. So that means the area of the steel reinforcement AST1, AST2, ASC can be found using the simple relations given here. Okay. So AST1 means it is for balanced section. Find out the moment, limiting moment of resistance, equate it and get the value of AST1. Okay. Then find out the MU2 and equate T2 into Z, find out AST2. Similarly, MU2 equal to CS multiplied by Z, you can find out ASC. Or otherwise also, you can find out if one steel reinforcement is known, you can find out other steel reinforcement by using T2 equal to CS. So sometimes if AST2 is known, you can find out ASC, or ASC is known, you can find out AST2. So these are the relations in doubly reinforced section. These are the relations in doubly reinforced section. So I'll go through once again a bit fast. Doubly reinforced beam can be split into two sections. One is singly reinforced balanced section plus tensile steel reinforcement, additional steel at bottom, compressive steel at the top, and these are the two associated diagrams. And for computing the neutral axis, we use total compressive force equal to total tensile, Cc plus Cx equal to T, and accordingly you will get Xu. Once Xu is known, you can find out the strain in the steel and also Xu maximum. And accordingly, by comparing this, whether it is under reinforced section or over reinforced section is known, and accordingly compute the moment carrying capacity. Or otherwise, area of the steel reinforcement may be the question. How to calculate the AST? AST1 means area corresponding to the balanced moment of resistance, and accordingly find out AST1. And similarly, getting MU2, find out AST and also ASC. So these are the various equations in case of doubly reinforced sections. Now we are going for flanged beams. Flanged beams. Why again flanged beams required? In the case of doubly reinforced section, even if you provide more quantity of tensile reinforcement and also compressive reinforcement, what is going to happen here? Here Xu reaches to Xu maximum, that is balanced. Once Xu reaches to the Xu maximum, there is no further increment of moment due to additional steel. So additional steel can be provided any amount of steel can be provided. But if the resistance of the tensile steel is more, compressive resistance also should be more, so that it will take more moment of resistance. But by providing more steel reinforcement, we can improve the tensile load carrying capacity, but there is no improvement in compression carrying capacity because of the limited area. There is no further improvement. So for that purpose, by increasing the compressive area, we go for T-beam or flanged beam. So here you can look at the not only this rectangular portion, the portion outside of the rectangle will also contribute to the compressive resistance. That means the area provided on compression side of the beam is more, so more compressive resistance will be obtained because of providing the L beam or T beam or flanged beam. So this is called the flange. So mainly flanged beams are required to increase the compressive resistance of the concrete. To increase the compressive resistance of the concrete, we are providing the flanged beams, and we can provide suitable reinforcement of large number so that it will be under reinforced section or balanced or over reinforced section. And sometimes even this is also not enough, we go for again compression steel reinforcement. Again compression steel reinforcement. So what are the contributions here? If it is, this is called doubly reinforced flanged beam. Doubly reinforced flanged beam. In this case, how many compressive forces are there? Compressive force by web. By web means this particular area. This particular area, because this is same as that of singly reinforced balance section. Earlier we call it as CC, compressive resistance of concrete. Now we are calling it as CW, the same magnitude, everything same, CW, compressive resistance of the web. Plus, and there is a flange on either side, so compressive resistance of the flange. Compressive resistance of the flange. And one more, compressive steel. So you can also write CS, which is equal to other side tension reinforcement T. So that means in earlier case, singly reinforced, we are using CC equal to T only. In case of doubly reinforced, we are using C and also CS, which is equal to T. Now in case of singly reinforced T-beams, CW plus CF will be equal to T. This is called singly reinforced T-beam because there is no compression steel. Whereas it is called the doubly reinforced T-beams. Doubly reinforced T-beam means web, flange and steel. Web, flange, steel. Singly reinforced means web, flange, no steel. No steel. So this is how the equations are to be written. This is how the equations are to be written. So the T-beams are used. The T-beams are used for increasing the compressive resistance of the concrete. And you know that nowadays most of the structural members are monolithic. Most of the structural members are monolithic. That means the rectangular beam and also the slab. This is called the slab. This is slab on one side. It is also called slab on other side, and it will be contributing to the strength for the beam. So when the slab and beams are monolithic, and monolithic construction is possible. So all the beam and slab combination structures are always T beams or L beams. T beams or L beams. If the beam is at the middle, then it is called the T beam. If the beam is at the end, it is called the L-shaped beam. So whether it is L-shaped or T-shaped, the procedure is one and the same. So now you need to understand how to calculate all these parameters. Now let us go for it in general. Now why flanged beams are required? Already I told you, to improve the compression resistance of the concrete. The concrete area will be increased on the compression phase by providing compression flange. And the nomenclature for this will be small bf, suffix f. So that means b suffix f means width of the flange. B means width, small f means flange, and capital D depth. Small f means flange. So depth of the flange is df, and overall depth is d from top to bottom. And small d is effective depth, means center of the steel reinforcement to the extreme compression fiber. Now Now, when it will be called as a T-beam. So the code has given some guidelines. It will be called as T-beam. It has to follow certain norms. So here what is going to happen here is certain things it has to follow. A slab which is assumed to act as compression flange of a T-beam or L-beam, compression flange for T-beam or L-beam shall satisfy the following. Number one is, the slab shall cast integrally, that is monolithic construction must be there. When monolithic construction is there, or otherwise perfect bond between the beam below the slab and also the slab, then only it will be called as T-beam. This is one condition that is to be satisfied. So both slab and also beam must cast simultaneously, then that will be called as T-beam. And also the second one should also satisfy. If the main reinforcement of the slab is parallel to the beam, transverse reinforcement provided as such a reinforcement must be 60%. The meaning of it will be, I'll explain a little bit here. So you can just look at here. This is the overall size of the hall, and this is one beam, then another beam. These are the beams that are provided in a hall. Beams that are provided in a hall. Like this, and this is the T-beam. So here effective depth is to be considered. What is that you are going to do is center to center, not center to center, certain portion. So from here to here, this will be acting as a T-beam. If you take the cross section, it will be like this only. It will be like this. So the beam at this level is called the T-beam. T-beam. So part of the slab one side and part of the slab another side will act as a flange, and it is called T-beam. So for this also it is T-beam, it is also T-beam, 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 but at the end it is called L-beam. So what is going to happen here? The flange will be only on one side, so it is called L-beam. Similarly, for this end beam is also having this end beam is also having okay. This L beam is also having flange only on one side. So this is also called as L beam. So all end beams in a hall are L beams, and all intermediate beams are called the T beams. So these beams are to be designed for the T beams. So here what is going to happen is we are going to provide tension reinforcement in the slab. Tension reinforcement in the slab, which is called AST. So 60% of the reinforcement must be provided at the top. So this dotted line is reinforcement to be provided at the top. So this dotted reinforcement must be 60% of AST. 60% of AST. So that means the slab and beam must cast monolithically. That is one condition. Another condition is the area of the reinforcement that is designed for the slab is AST, and at least 60% of that reinforcement is to be provided at the top of the beam, so that it will act as a tension reinforcement. So these two conditions are to be satisfied, then only it will be called as T-beam. Then only it will be called as T-beam. So now look at here the second line. If the main reinforcement of the slab parallel to the beam, transverse reinforcement shall be provided as shown in figure such that it shall not be less than 50% of the main reinforcement at midspan of the beam. So, in the slab, if the reinforcement is AST, at the top it must be provided at least 60% of it. So, then only it will be called as T beam. And effective depth. Effective depth, normally on either side of the beam, half the slab and half the slab can be considered, but the total width is not effective. And because of the stress variation across the length of the flange. So that's why effective width of the flange has given, code has given some formula. Effective width is restricted to L0 by 6 plus BW plus 6DF. L0 is center to center. L0 is the distance of the points of contraflexion. In case of simply supported, L0 is nothing but effective span, and BW is the width of the web, and DF is the depth of the web. Sometimes it may be a numerical question. For certain data, what is the effective width of the flange? What is the effective width of the flange? That may be the question. Or some for L beams. For L beams, it is same as that of the previous one with minor changes. Because T beam means it is a beam on both the sides, flanges on both the sides, and BF will be equal to L0 by 6DF. Whereas if it is L beam, here L0 by 12, and instead of 6DF, now it is 3DF. So this is for L beams. And third one is, it is for isolated beams. Isolated beam means what is the meaning of it? Sometimes the beam may be used for sometimes it may be used for say cycle shed. Sometimes it may be used for cycle shed. What is going to happen here? This is the ground level, and here it is car parking can be used below this, or scooter parking or cycle parking. And this is flange one side, this is flange on other side, and this will be the web section. This is the web section, and of course below it a column and the other one. So this is called the isolated T-beam. Isolated means independent T-beam. Independent T-beam. If the isolated T-beams are there, then the effective width is L0 by L0 by B plus 4 plus BW. So this is the formula for L beam and also T beam. You have to remember these formulas because there is no concept oriented one, and it is empirical formula given by us for IS 456, and the numerical questions may be basing on these formulas. And all these parameters. L0 means distance of the 0 points of moments in the beam. The distance is for example, for case of simply supported beam, so it is L0. L0 is nothing but the effective span. And in case of continuous, it is 0.7 times. In case of continuous beams, L0 value is 0.7 times of L for continuous beams. For continuous beams, because for continuous beams points of contraflexion will occur at a distance of 0.7 times L approximately, and that's why we are taking L0 as 0.7 times of L. Now let's go for the analysis like previous case. What is the analysis? Of course it is given for continuous beam 0.7 times the effective span. Now we are going for analysis. So in the analysis, it is you can imagine singly reinforced, doubly reinforced. Now imagine the T-beam. Imagine the T-beam. So observe what are the changes from singly to doubly, from doubly to T-beams. So that overall concept for all the three will be there in your mind clearly. So first one is, that neutral axis may be lying in the flange. You can look at here. sometimes there is a possibility that the neutral axis may be within the flange or outside the flange, within the flange or within the web. So one of the assumption, when the depth of the neutral axis lies within the flange. So when the depth of the neutral axis lies within the flange, this is the stress diagram. That means neutral axis is at this level. How it will act when the steel is less, when the steel is less and contribution of the area of the concrete is very large, then the neutral axis may fall in the flange itself. So in such a case, what is this called? What is this? You can imagine that if the beam is of such a width and the neutral axis is somewhere here, neutral axis is here. The moment carrying capacity of this T beam, the moment carrying capacity of the T beam is same as that of rectangular beam. This rectangular beam, you can look at here, moment carrying capacity of this beam is same as that of rectangular beam of effective width, that's all. So that means, what is the meaning of it? Below the neutral axis, the entire area is neglected. Whether it is a T-beam or rectangular beam, this entire area is not considered. We are considering only the area above, and it is BF, B suffix F. So in this particular case, when the neutral axis lies within the flange, it will be just like a rectangular beam. So the moment of inertia or the analysis is same as that of rectangular beam of width B suffix F. The analysis is same as that of rectangular beam of width equal to B suffix F. So that means if it is rectangular, what are the things? C equal to T. What is C? 0.36 FCK B. In place of B, now the B means it is B suffix F multiplied by XU will be equal to 0.87 Fy into AST. This is the equation that you have seen in for singly reinforced section. The same thing will be used when the depth of the neutral axis lies within the flange. The depth of the neutral axis lies within the flange. So it is as good as rectangular beam. And another one, when the neutral axis lies within the web. So the neutral axis may be lying in the web. If the neutral axis lies in the web, we are considering two different parts. Concrete of simple web section. You can see that it is web section because it is same as that of singly reinforced concrete. And another part, so this is part one. Another part is the flanges on either side. So what are the various forces here? One force is C suffix S, C suffix F. That means compressive resistance of the flange. Where this compressive resistance of the flange occurs, it will be at the center of this flange. And another one is CW. Where this CW occurs, CW means compressive resistance of the web. This is also nothing but CC, compressive resistance of the concrete, which is 0.36 FCK B into XU. Originally this is singly reinforced. Now in case of flange, this is CF is the additional force. So CF and CW are acting and T will be the tensile force. But here one more thing is there, because in case of in the first case, what is going to happen? 3/7 of XU means this is the rectangular depth of the stress block. This rectangular depth of the stress block is within the DF value. You can look at 3/7 of XU is less than DF. DF means depth of the flange. The meaning of it will be already written. The depth of rectangular portion of stress block this one, depth of the rectangular portion of the stress block is less than the depth of the flange, is less than the depth of the flange. That means what is going to happen? Rectangular portion of the stress block 0.45 FCK is for some height only, is for some height only. For the remaining height, what is going to happen? 0.45, and it is decreasing. It is decreasing. So it is decreasing. So accordingly, XU is less than 7 by 3, and finally DF equal to 0.43 XU. So that means what is going to happen is the entire depth of the flange is not having uniform stress. The entire depth of the flange is not having uniform stress, because uniform stress is only for certain height, and after that it is decreasing. It is decreasing. So what we do is effective depth now will be, effective depth of the flange now will be YF. Effective depth of the flange now will be YF. So that YF will be equal to 0.15 XU plus 0.65 DF, and it should not be more than, it should not be more than or equal to, it should not be more than DF value. DF value. So now in the original way, C is equal to T means how many compressive forces are there? Compressive force of web, compressive force of flange equal to T. What is CW? CW means compressive resistance of concrete only. 0.36 FCK BW. Here earlier we are using B. Now it is BW means web. BXU. CF means what is the stress in flange? 0.45 FCK. What is the area? B suffix F minus BW into YF. The depth of the concrete, you know that there are two different parts here. You know there are two different parts. So already this area is considered. What is the leftover part? This part will be this part, and this part will be the flange. What is this part? Total is B of B suffix F minus BW by 2. This is also B suffix F minus BW by 2. What is the total flange? Total flange is nothing but B suffix F minus BW. So that is the total effective width of the flange. And what is the depth? Depth is not DF. Depth is not DF. It is now YF value. Capital YF. Depth is now YF value. So, and is equal to T means 0.87 FYAST. Substitute and get the value of XU. In most of the questions in the examination, computation of XU is the more important question, because up to here it will take some little amount of time, and further the question may not be there in the exam, and you need to understand here in case of singly reinforced T-beams, web part, flange part equal to tension. And what is web part, what is flange part, and what is T, accordingly find out XU. And once XU is known, XU maximum will be in the same procedure as that of earlier, that is 0.53D, 0.48D, 0.46D. And moment of resistance is as usual 0.87 FYAST into D minus A. D minus A. It is the same as that of already seen earlier. So A is the distance from the extreme top fiber. It is CW. Its distance is 0.42 XU. Compressive resistance of the flange is from YF by 2, from YF by 2, and CW by CF. And if the section is over reinforced, then first term is a balanced moment carrying capacity. You know that it is balanced moment of resistance. What is the second value? Second value is compressive force in flange. What is compressive force in flange? 0.45 FCK BF minus BW into YF. And what is lever arm? D minus YF by 2. D minus YF by 2. So what's going to happen here is I'm going to draw the diagram once again here. So this is T, whereas here for the flange CF and for the web part CW. So now it is nothing but what is the distance of CF? CF distance top is D dashed. From CF to top it is D dashed, effective cover. Effective cover. So CF to T it is D minus D dashed. D minus D dashed. D minus D dash. What is CW? CW is nothing but it is D minus 0.42 XU. So here it is wrong, please. This equation is okay. It is flange. It's okay. This is nothing but YF by 2 and it is okay. It's okay. D minus YF by 2. So what is this distance? It is YF by 2 and this is also D minus YF by 2, D minus YF by 2 and this equation is correct. So what is that we are doing? You know this distance CF multiplied by that distance. This is nothing but D minus YF by 2. That we are writing. And CW multiplied by D minus 0.42 XU. So remember, first term is always the singly reinforced term. Second term is only for the flange. Second term is only for the flange purpose. Now, what is going to happen in this case is in this case of the flange. This is the T beam, and what is going to happen here is the neutral axis will be at this level. So this is the depth of the rectangular portion DF, where DF. What is the stress? Stress will be more. You can see that this height is more than DF. You can write 3 by 7 of XU is more than DF. So DF is less than 0.43 XU. It is sometimes in the examination important. DF is less than or DF is more than, etc. So what is the meaning of it? If this is the case, what is meaning is at every part of the flange, the stress will be equal to 0.45 FCK. 0.45 FCK. If this is the case, we are going to use only DF because every point of the DF is same as 0.45 FCK because this vertical depth is same. So here also use the same condition, C equal to T. C means web. This is C means the two parts C web plus C flange will be equal to T. C flange means 0.45 FCK B suffix F minus BW into DF equal to 0.87 etc. You will get XU value. If it is under reinforced, the routine procedure that you have seen earlier. If it is over reinforced, the procedure is also the same. Only thing is, in previous case, this is YF used. Now we are going to use DF value. Except that there is no change in computing the moment carrying capacity of T-beams. So here in case of T-beams, I will spend 2 minutes regarding the overall. What is going to happen here is, just try to understand this. Here we are going to take the very first case will be the depth of the neutral axis is within the flange. So in such a case, mu will be nothing but 0.36 FCK B into XU into D minus 0.42 XU. That means it is same as that of rectangular beam having width equal to B suffix F, except that nothing. And other cases are, you can look at here, the neutral axis lies within the web. But what is going to happen here is, this is called the depth of the rectangular portion, and total stress will be 0.45 FCK. 0.45 FCK is constant up to here only, and beyond that it is varying. Since the stress is not constant, what is going to happen is the equivalent depth will be taken as YF. That equivalent depth is nothing but 0.15 XU plus 0.65 DF, and it should not be more than, in any case, DF value. Because here what is going to happen, rectangular portion of the stress block, what is rectangular portion of stress block? 3 by 7 of XU is less than DF value. Rectangular portion of the stress block is less than the depth of the flange. In such a case, YF is to be taken. And in this case, what is going to happen? This is here, what is going to happen? This is one force. This is called the CF, and it is another force. It is called CW. CW means the entire web is considered like this. So important thing here is CW means for all it is same. For whether it is singly reinforced, doubly reinforced, everything is same. CW means 0.36 FCK BW into XU. Earlier we called simply it B, now it is BW. And what is the associated lever arm for this? For this lever arm will be D minus 0.42 XU. If you want moment, multiply this and this. So that you will get moment. Similarly, what is the compressive resistance of the flange? So in the flange, what is the stress? 0.45 FCK. What is the area of the flange? What is the remaining part of the flange? Remaining part of the flange is BF minus BW. And what is the height? Height is now YF. So what you do is put it to YF. So this is the compressive resistance of the flange. What is its lever arm? The lever arm will be equal to D minus YF by 2. Because CF to top is YF by 2. So the lever arm is now, it is total depth minus YF by 2. If you want moment, what you do? CW into D minus 0.42 XU, CF into D minus YF by 2. That's all about it. In another case, what is the other case? Like this. In other case means when 3 by 7 XU is greater than DF, in that case what you do? CW is the same, there is no change. What is that? 0.36 FCK B XU, and this is also same, that is D minus 0.42 XU. Okay, this is force, that is lever arm. And what is the CF value? CF is 0.45 FCK BF minus BW, because this is the remaining length. What is the depth now? Depth is DF. Here we are using YF, Now here directly we are using DF. And what is the lever arm in this case? Lever arm in this case is D minus DF by 2. D minus DF. If you want movement, for these are the forces and lever arms. If you want movement, what you do? This force multiplied by lever arm, this force multiplied by lever arm, so that you will get the moment. That's all about it. So here one term is for the web, another term is for the flange, one more term is for the compression steel if it exists. Compression steel if it exists. Okay. So now let us go for doubly reinforced beams. So in this case, how many forces are there? 3. One is CW. Okay, I will write once again here. Compressive resistance of the web. What is compressive resistance of the web? 0.36 FCK BW into XU. That is compressive resistance of the web. Because you can look at compressive resistance of web number 1. What is number 2? Remaining area of the flange. So flange means compressive resistance of the flange is 0.45 FCK, because you know that the stress here will be 0.45 FCK multiplied by remaining distance. B is suffix F minus BW multiplied by DF. And what is one more term? Compressive resistance of the steel reinforcement. What is compressive resistance of steel reinforcement? Whatever the formula used in doubly reinforced section is same now. FSC minus FCC multiplied by ASC. If you know all these, what are the corresponding lever arms? Lever arms are D minus 0.42 XU for the first one. The second one D minus DF by 2. The third one D minus D dash. These are the 3 lever arms. If you want force, you can find out. If you want movement, you multiply all those. That's all about the total T-beams. By understanding these 3, you will get everything. So what normally you will do in the examination, if at all a question, that will be basing on this. Total compressive force equals total tensile, and put all these forces here and find out XU value. And if it is under reinforced section, T into D minus A, and that A value will be computed using this formula. Or otherwise, if it is over reinforced section, moment of resistance is because of the compressive resistance due to web, and resistance due to flange, resistance due to steel. So all the 3 terms are just now I told you. Multiply this force multiplied by distance, second force distance, force multiplied by distance, and you will get these formulas. That's all. That's all about the total conceptual theory in flanged beams. So what you do is, this entire concept is not tough. Only thing, you try to understand and read the thing from singly reinforced to doubly reinforced, doubly reinforced to T-beam, singly reinforced T-beam, singly reinforced T-beam to doubly reinforced T-beam, and observe what are the various changes that are being takes place. And accordingly, you can find out the various terminology and everything without any difficulty, because everywhere see compressive resistance of web, compressive resistance of flange, compressive resistance of steel. Whatever the compressive resistance of steel used in doubly reinforced, same. And CW, it is same as that of singly reinforced. And flange means it is the resistance due to flange. That is the additional part in case of flange beams. So here you can summarize it: singly reinforced beams, doubly reinforced beams, singly reinforced T-beams, doubly reinforced T-beams. You can look at singly reinforced T-beam. In singly reinforced T-beam, you call CC, compressive resistance of concrete. In doubly reinforced beams, The compressive resistance is CC and also CS. Both the terms appear. And singly reinforced T-beam. Singly reinforced T-beam means compressive resistance of web. That means CC, CW both are same. And another one is compressive resistance of the flange because there is no compression steel. In case of doubly reinforced T-beams or doubly reinforced L-beams, compressive resistance of web, compressive resistance of the flange, compressive resistance of steel will come into picture. That's all. In case of this, this will be equal to T. In case of doubly reinforced, sum of these two equal to T. In case of singly reinforced T-beam, sum of these two equal to T. In case of doubly reinforced T-beam, sum of these terms will be equal to T. And you know all these terms. CW 0.36, FCK, B into XU. CF means 0.45, FCK, BF minus BW multiplied by DF. And CS is nothing but FSC minus FCC into ASC. And T is nothing but 0.87 Fy AST. That's all. Use appropriately all these formulas and also associated lever arm distances so that singly reinforced, doubly reinforced, singly reinforced T-beams, doubly reinforced T-beams, everything covered in a single page here. Okay. Now let's go for some numerical questions. A reinforced concrete rectangular beam of size 250 by 600 mm overall, you can look at the diagram also, 600 mm overall, is reinforced with 3 bars of 25 mm on tension face at bottom. You can look at 325 bottom and 2 bars of 16 at the top. So you can look at this diagram clearly given. The effective cover for tension and compression reinforcement are 50-40. So effective cover for tension reinforcement 50, effective cover for compression is given 40. And here M20 grade of concrete given, so FCK equal to M20. And FE 500 is given, FY will be equal to 500. That's all. The question is, the depth of neutral axis is. The depth of neutral axis is. That's the question. So if you want to calculate depth of neutral axis, what you do? This is a doubly reinforced beam. C is equal to T means how many C values are there? CC plus CS will be equal to T. What is CC? 0.36 FCK B into XU. What is it? CS FSC minus FCC ASC into is that's all 0.87 FI AST. Okay. Here a small mistake, please. Here it is 250. In the problem, it's a small calculation. FE 250 is considered. So if FE 250 is considered, FSC is nothing but 0.87 Fy. Already I told you, for mild steel bar, FSC will be full value, that is 0.87 Fy. And FCC means 0.45 FCK, 0.45 into 20, this is 9. So now FSC is known, FCC also known. Substitute all the values except X value, and X value will be 131. Okay, so here important thing is how to calculate FSC, how to calculate FCC. FSC is nothing but 0.87 times Fy in case of FE 250 grade steel only. FCC is 0.45 FCK. Okay, if the grade of steel is other than this, I will tell you how to calculate this. So basing on this XU value, this may be the question in the examination, or sometimes extension may be. Find out XU maximum 0.53D because it is FE 250 and 295. So XU is less than XU maximum, it is under reinforced. When it is under reinforced, the moment carrying capacity will be equal to 0.87 Fy AST into D minus A. Already it is here. Because when it is under enforced, steel will be governed. Steel will be governed and accordingly can use. And A is the distance of the CG of compressive force from the extreme compression fiber. So CC into 0.42 XU from the top, CS into D dash from top divided by CC plus CS, and accordingly find out CC value first. Then CS value FSC minus FCC ASC, and then A, and then moment carrying capacity 0.87 Fy AST D minus A. So you will get 159.5. So here for computation of this value is a little bit tedious. So instead of this, in doubly reinforced beams, either you can use the formula with the tensile reinforcement, or otherwise you can use the formula with the compression reinforcement also. Just now I told you. So that's why here R. So the problem can be solved by using directly this equation, whether it is under reinforced or over reinforced. Even for over reinforced also this can be used. Over reinforced also this can be used, and or otherwise this. So it is involving some calculation. It may take some time. So always you go for using what is this first term? First term is nothing but CC multiplied by Z1. Z1 is D minus 0.42 XU plus CS multiplied by D minus D dash. CS means FSC, FCC, ASC, D minus D dash, and accordingly you got it 159.5. Otherwise also 159.5. So either you do in the second way or first way. First way is always easy. So you always move in for computing the moment of resistance by using only compressive forces. By using only compressive forces, no need to go for tensile forces. Okay, the next problem, it is also with the 250. Only the problem here is 6 bars of 25 used. In earlier problem, you know that it is 3 bars of 25. 3 bars of 25. All other data is same. In this case, 6 bars of 25 and 3 bars of 16 are used. You can look at. I'm sorry again, this is 2. So you can look at the diagram. 2 bars of 16 mm, 6 bars of 25 mm on tension phase, and effective cover is 530 mm, effective cover is 70 mm, and effective depth is 530. For tension reinforcement, if 40 mm is the effective cover. Okay. So for this particular diagram, what is the first question? First question will be, what is the first question here? First question will be, what is the depth of neutral axis? To get the depth of neutral axis, C is equal to T. And use the same way as earlier, FSC, FCC, everything. And finally, you will get 308. 308. The same formula, whatever the problem that you have seen first one, it is same as that of this. And once it is known, find out XU maximum, it is 280. XU maximum 280, but actually is 308. So XU is more than XU maximum ORS, over reinforced section. In over reinforced section, use the same formula. I told you, I'm again telling, whether it in case of doubly reinforced section, whether it is singly reinforced or doubly in case of doubly reinforced section, whether it is over reinforced or under reinforced, use only the formula relating to compressive forces. That is easy. That is easy for computation. Okay, anyway, here it is over reinforced. When it is over reinforced, the first term will be 0.148 FCK BD square. And accordingly compute it. The second term is FSC minus FCC ASC D minus D dash, and accordingly find out the total moment carrying capacity. Sometimes the question may be, what is the strain in compression steel? What is the strain in compression steel means? Strain in compression steel means, what is the strain at this point? What is this strain? Already you know the formula. ESC will be 0.0035 XU minus T by XU. Here it is over reinforced section. So X is limited to XU maximum, and accordingly this will be the strain. Accordingly this will be the strain. Sometimes this may be the question. Now look at this clearly. A reinforced concrete rectangular beam of size 250 by 600 mm overall. You can look at 250 overall is 600, is reinforced with 6 bars of 20 mm on tension phase. These bars are 6 of 20 mm dia on tension phase. At an effective cover of 70 mm. You can look at 70. The characteristic strength of concrete and steel are 25 and 500 respectively. The strain and associated stress values for the steel reinforcement is given as below. Given as in table below. Okay. So strain values and associated stress values. For the balanced section, the area of compression steel reinforcement required is, for balanced section, what is the moment carrying capacity? What is the moment carrying capacity for the balanced section? You know, since it is Fe 500, XU maximum is 0.46D, so that it will be this. What is MU limiting? MU limiting is for Fe 500, it is 0.133 FCK BD square, accordingly 233.5. And MU limited is known. MU limited is known. What is that you have to calculate? What is the question here? For the balanced section, area of steel reinforcement is, so MU limited equal to this one. Already MU limited, you know that it is 0.87 Fy AST1 D minus 0.42 XU, and this will be the steel reinforcement for balanced section. And AST2 additional tensile steel is total steel minus AST1. Total steel is 6 bars of 20. 20 means 314 is the area of each bar, and 629 is the additional steel, tensile steel. What is the strain in compression steel? Strain in compression steel is, this is the formula that you know, and it is 0.00292. For strain 0.00292, what is the FSC value? In case of mild steel, FSC is nothing but 0.87 Fy. For others, for that is for Fe 415 and for Fe 500, FSC is not equal to 0.87 Fy. It is basing on the strain values. So for 00292, in the question itself it is given strain and also stress. In the table it is given, but this is the your calculated value 292. What is the stress? 417.7. Stress in steel is 417.7. So what you do in the problem? So you have to use FSC will be equal to 417.7 Newton per mm square. So in the examination, the required data will be given in the form of a table or the charts. Accordingly, you need to get it. For mild steel only, it is 0.87. For all other things, the stress value depends on the magnitude of the strain. And once it is known, already you know T2 equal to CS 0.87 Fy AST2. Like that, from this you can find out ASC. So area of the compression steel reinforcement. So these are based on the basic fundamental relations of the forces and also its associated moments. Now this is another question. The question is similar. 5M. I'll read the question here. Question is simple. It's a beam with M25 grade of concrete and 500 grade of steel reinforcement. Size is given 250 by 600 and effective cover to compression steel 40 mm and effective cover to tensile steel reinforcement 70, and it is given if the area of tensile steel reinforcement required for singly reinforced balanced section is 1255 mm square, then the area of compression steel reinforcement for balanced is. So here what is going to give here, the total steel reinforcement is 2000 millimeter square. 2000 out of this 1255 millimeter square is the steel reinforcement corresponding to the balanced section. That means this is AST1 and 2000 is the total steel, so AST2. What is AST2? AST2 is nothing but total minus AST1. This is AST2. What is the question? Question is area of the compression steel reinforcement is. The question is what is ASC? What is ASC means? T2 will be equal to CS. Additional tensile steel resistance will be equal to compressive resistance of the steel reinforcement, and accordingly use this formula. So 0.87 Fy AST equal to FSC minus FCC ASC. Here what is FSC? FSC is based on the strain. What is the strain? 0.00292. If it is 0.00292, what is the stress? 417.7. It is given along with the question. Okay. So now that value is known. What is FCC? FCC is normally 0.45 FCK. So here ASC is not known. You can find out the area of the compression steel reinforcement. So here actually it is the middle of the question. If you know the overall idea of the solving a very big problem, and if the data is given and a small question is asked in that, you should understand the total procedure. You should know the total procedure of computing the area of compression and also tensile steel reinforcement. Okay, now look at T-beams. A reinforced concrete T-beam consists of 1200 mm by 100 mm size of flange. So BF, B suffix F 1200, DF 100 mm and web of 250 by 500 mm. 250 by 500 mm below the flange. Below the flange means from here only it is 500. Here only it is 500, but clarity is given such that overall depth is 600. Overall depth 600 means from top to bottom it is equal to 600. It is reinforced with 3 bars of 25 mm dia on tension phase. You can look at 3 bars of 25 mm dia on tension phase at an effective cover of 40 mm. So this is called the effective depth. The characteristic strength of concrete and steel are 25 and 415 respectively. The question is, what is the depth of the neutral axis? What is the depth of the neutral axis? So normally, when the steel reinforcement is small, there is a possibility of neutral axis within the flange. Here, when the steel reinforcement is small, there is a possibility of depth of the neutral axis within the flange. So, because of only 3 bars of 25, it's a small reinforcement. So, initially what you do is assuming that neutral axis lies within the flange. If the neutral axis here lies within the flange, what is going to happen? C into T. What is C? C is for this much width of the flange. This much width of the flange. So instead of B, it is B suffix F, XU and remaining. And B suffix F is now 1200. Accordingly, substitute all the values 49. So what is the depth of the flange? 100. So whatever the assumption that you consider, that is true. So XU is less than DF. It is lies within the flange only. It is lies within the flange only. When it is lies within the flange, what is the moment of resistance? Moment of resistance is same as that of rectangular beam of width equal to BF, width equal to B suffix F. So moment of resistance is 0.36 FCK. This is important. B suffix F, XU, D minus 0.42 XU. So that means when the neutral axis is lying within the flange, the moment carrying capacity is same as that of rectangular section of width equal to B suffix F, and substitute all the values, you will get ultimate moment of resistance equal to this. Then a reinforced concrete T-beam. A reinforced concrete T-beam consists of 1200 by 100 mm size of flange, and because I took the same size, because you need to understood what is the difference from one figure to the other figure by changing the reinforcement from 3 bars to 6 bars, etc. It's only for the sake of understanding the concept. I mentioned the size, everything is same. So here the question is, this is a T-beam, 1200 effective width, 100 effective depth of the flange, 6 bars of 25 mm dia used at a effective cover of 70, width is 250, effective depth is 530. This is the overall question given in the lines. And characteristic strength for concrete 25, for steel 500. Now the question is, the depth of neutral axis is. So what is the depth of the neutral axis? Depth of the neutral axis means naturally C is equal to T. What is that you will assume? Normally when the reinforcement is more, it will be lying in the web portion. But if you want, you can also check whether it is there in the web or in the flange. So initially we are assuming that neutral axis lies within the flange. It's only assumption. And C equal to T, accordingly if you calculate 118. What is 118? It is more than 100. It's more than 100. So this assumption is wrong. So the neutral axis is not within the flange. It lies outside the web. It lies within the web or outside the flange. So next what you do, one more condition is there. What is that one more condition? 3 by XU is less than DF. This is one case. Or 3 by 7 XU is more than DF, another case. These are the two different cases that are associated. What is 3 by 7 XU? Depth of the rectangular portion of the stress block is less than the depth of the flange. If this is the case, we have to use YF value instead of DF. If the case the rectangular portion is more than depth of the flange, in this case we are going to use DF as it is. That is the only difference between these two. And here we are assuming that the rectangular portion of the stress block is less than the thickness of the flange. When it is less than the thickness of the flange, you have to use YF value. So what is YF value? YF equal to 0.15 XU, 0.65 DF is the value. And ultimately for depth of the neutral axis, compressive strength of the web, compressive resistance of the flange equal to T. So you know this is one equation. It's another equation and it is equal to tension. Substitute all the values. Substitute all the values and in place of this YF, you have to substitute 0.15 XU plus 0.65D. You can look at 0.15 XU, 0.65D. In all these, XU is the only unknown value, so you can find out that XU value. Once XU is known, then find out this YF value. So YF is 87.8, which is less than DF. What is DF? 100. It is less than DF. So your assumption is correct. What is the assumption that you consider? Rectangular portion of the stress block is less than the depth of the flange. That assumption is correct. Once it is correct, then this value of 157 is alright. Then XU maximum according to this 243. So compare these two. So XU is less than XU maximum. The given section is under reinforced. Whenever it is under reinforced section, then moment of resistance is governed by the two terms. What are the two terms? CW, that is web part, and also the flange part into D minus this. So use this appropriately because this is the compressive force CW, its lever arm. Compressive force of the flange multiplied by its lever arm and substitute. Finally, you will get the moment carrying capacity of the section. So only understanding this formula is more important. So the next question, it's also similar. Here what is going to happen is you just look at this. The characteristic strength values are 25 and 500. The effective cover, the question is area of tensile steel reinforcement corresponding to the balanced section. Corresponding to the balanced section. So corresponding to the balanced section means you know that XU is going to become XU maximum. That's the only change. So XU maximum is now 243.8. And since it is singly reinforced T-beam, so CW plus CF equal to T. This is the equation that you know. Put CW in place of X, it is now XU maximum because it is balanced section. And in place of CF, write the entire equation. And T, everything is known except the area of the steel reinforcement. Sometimes the question is very simple for computing the area of steel reinforcement for the balanced section. For the balanced section. Like that, small questions will be there. One more. So this is a question doubly reinforced section. So the question maybe appears to be big. Here finally I'll tell you the entire question. Width of the beam given BF 1200, DF 100, then effective depth 530, effective cover to tension reinforcement 30. This and area of the compression steel 600, area of the tensile steel 4000 mm square. 4000 mm square. So what is the question here? Depth of the neutral axis is. You know here the reinforcement is considerable. Reinforcement is considerable, and assuming that it is neutral axis lies within the web. So what are the various forces? Compressive resistance of web, compressive resistance of the flange, compressive resistance of the steel, because compression steel also included equal to T. So already I told you in theory what is CW, what is CF, what is CC. Write all the values. Write all the values. And equal to 0.87 FYAST. Substitute the values, you will get XU equal to 189.3 mm. This may be the question sometimes. If the question framed is maybe big along with the sketch, but the solution is simple by equating total compressive resistance to the tensile resistance. And here important thing is writing each and every individual term. Once you know the individual term, then substitution will give you exact value of it. In the problem itself, it is given assuming that FSC equal to 420. FSC equal to 420 means use FSC value as it is, that is given in the problem. And here it also given DF is less than 0.43 XU. So naturally DF will be used, not YF value, not YF value. So according to the problem, equate the total compressive resistance of the concrete to tensile resistance of steel, and you will get the XU, depth of the neutral axis. And that's all. In case of doubly reinforced case, the moment carrying capacity is a little bit tough, and if required, you can also calculate, otherwise not required for study purpose. And these are the various questions on doubly reinforced and also T-beams. This is the question appeared very recently in 2020. And I will tell only one or two problems so that the remaining questions you can go through, and if there is any difficulty you can post the raise the questions by means of Gmail, through Gmail. I will read the question, very recent question given in the examination. The cross section of reinforced concrete beam having an effective depth of 500 mm. You can also look simultaneously the figure. Effective depth of 500 mm is shown in the figure, not drawn to scale. The grades of concrete and steel are M35 and Fe 550. So it is M35 and Fe 550. The area of tensile tension reinforcement is 400 square millimeter. 400. It is given that corresponding 0.2% proof stress, the material factor of safety 1.5, and yield strain Fe 550 is 0.0044. As per IS 456, what are all these values? This is partial factor of safety considered already in deriving all the equations. And this is the proof stress normally considered as per code. And this is the value of the strain. What is that value of the strain? Value of the strain will be computed. This is the strain corresponding to FYD, yield stress, that is 0.87 times of Fy. So this value is also there in the table already. While discussing the singly reinforced beams, this strain table also given. It's not of that much use now. Okay. As per IS 456, limiting depth of the neutral axis measured from the extreme compression fiber. Limiting depth means the question is, what is XU maximum? That's the question. What is XU maximum? Limiting depth of the neutral axis measured from the extreme compression fiber. So how to calculate the limiting depth of the neutral axis? You just see that it is 0.0035 is the compression strain. But in the problem, it is given that the strain, yield strain of 0.0044. 0.0044. 0.0044 means normally the strain at this point will be ES is not less than 0.002 plus Fy by 1.15 ES. So if you calculate this, you will get that 0.0044. What is the question here? When strain in concrete exactly 0.0035, when strain in steel is exactly 0.0044, the depth of the neutral axis is called the XU maximum. That you know, it is a fundamental concept. The fundamental, when both strain in concrete and strain in steel reaches its maximum value, then the depth of the neutral axis is called the XU maximum. So what you do, this XU maximum divided by this ordinate 0.0035 divided equal to D minus XU maximum by 0.44044. That's all. From this, simplify it and get the value of the depth of the neutral axis. It is done already in singly reinforced beams. Already done in singly reinforced beams. Now the question, according to the question, you should act. Because the strain in concrete is fixed. Strain in steel is given. And depth of the neutral axis is at the limiting. So when both of these two reaches its permissible values, then the limiting depth of neutral axis occurs, and from the strain diagram you can find out. And even AST is given, it is not required. Sometimes the data given in the problem may be more than the required. But what is the question and how to calculate is more important from the point of view of the examination. So now let us look at another problem which is given in another exam. Two rectangular under reinforced concrete sections X and Y are similar in all aspects except that longitudinal compression reinforcement in Y is 10% more. So the size of the two beams, this is X, it is Y, size is the same, AST is the same, effective depth is same, width is same, everything is same. One case it is ASC, another case it is 10% more ASC. You can look at compressive reinforcement in section Y is 10% more. Which one of the following is correct statement? Which one of the following is correct statement? What is the statement? Section X has less flexural strength and is less ductile than section Y. See, normally steel reinforcement is more means it is more ductile. There is no doubt in it. There is no doubt in it. So this is the area of the steel reinforcement. Normally what is going to happen here, by providing 10% of compression steel, compressive resistance will be more. When compressive resistance is more, then the compressive resistance is more, then moment of resistance is also more, and this is for the case of Y. This is for the case of Y. That means section X has less flexural strength and less ductile than Y. So because reinforcement is less ductile, and in the second case C is more, moment carrying capacity will be more. And see the other options. Section X has less flexural strength, it is okay, but more ductile. Why more ductile? Less reinforcement means no question of more ductility. Here section X and Y have equal flexural strength but different ductility. No equal flexural strength. Section X and Y have equal flexural strength and ductility. No. So ductility depends on the amount of steel reinforcement provided. More will be the steel reinforcement, more ductile in nature. And in this case, since the compressive reinforcement provided is more, compressive resistance is more, and accordingly moment carrying capacity in Y is more. So like that the questions will be there. Here we can look at this is L beam. Whether it is L beam or T beam, both are one and the same. So here it will be taken as B suffix F, width of the flange. And effective depth is 570, overall depth is 650 and 350. Here what is the question? What is the question? The question here consists of two questions. The value of XU as per the limit state of method of design. So okay, you use the normal equations. C is equal to T. One is CC plus CF, compressive resistance of the concrete flange, equal to T, and accordingly get the value of XU. It's a routine. And another question for the same, the ultimate moment carrying capacity as per the limit state. So ultimate means find out the XU maximum and compare these two. It is under reinforced section, and accordingly use either formula related to the steel or related to the concrete, both are one and the same in case of doubly reinforced or T-beams, and you will get the moment carrying capacity of the section. Okay, similarly, several other small questions are there. Already the entire concepts are discussed. We go through all these small problems. The entire solution also given. Entire solution also given. So that if there are any doubts, that will be discussed a little later, and you can send the same to the mail. And tomorrow we'll go to the discussion on lecture on design for shear, torsion, bond, etc. So thank you. Today I'm closing the session. Thank you very much. Yes, ma close చేస్తున్నాను అయిపోయింది.